Today we're going to work on the Creating Quadratic Equations worksheet. At the top it gives you a story that says, suppose you are sitting in a hole 7 feet underground and you throw a ball straight up in the air. After a certain amount of time, the ball comes straight back down and you catch it. So if we were to draw a picture of that, you're in some hole in the ground. You throw a ball up in the air, and it turns around and it falls back down and you catch it. If we were to graph that, it would look something like this. The ball's going to start down at 1 second, it's going to gain, every second it's going to go up. Eventually, it's going to max out and it's going to begin to fall again, and that shape is going to be parabolic. So, you know the ball was at ground level at 2 seconds. So we know that at 2 seconds, the ball is level with the ground. And again, at 4 seconds, the ball is level with the ground. And we also know that at time 0, the ball is at -7. So number 1 says there are 3 points mentioned in the story. What are they in terms of x and y? So the points would be 0, -7, 2, 0, and 4, 0. So use those 3 points to create a quadratic equation. So turn your calculator on, go to Stat, Edit. My x's are 0, 2, and 4. And my y values are going to be -7, 0, and 0. And push Stat again, go to Calc. You want number 5, which is quadratic regression. And it's always a good idea to program this in your y1. So I'll do variables, y variables, function, y1, just in case we need that. And the equation is y equals -0.875 x squared plus 5.25 x minus 7. So if I graph that, push graph, and my graph is all mixed up. The window's a little bit wrong, so I want to push zoom. And number 6 on the zoom is zoom standard. And there's a picture of the position of the ball with respect to time. So now we need to graph the 3 points in the quadratic. So the quadratic looks like this. Number 4 says, how high did the ball travel above the ground? So I want to know, what is the maximum? What's the maximum value? So I'm going to push second calc again. Number 4 is maximum. It looks like it occurs at x equals 3. So for my left bound, I can choose 1. And then I could choose something like 3. My guess could be 2. And the answer is 3. 2.9999 is really just 3. So the y value at that point is 0.875. So the answer to number 4 is 0.875 feet. So that ball just barely, I didn't draw a very good graph. So here are those points. That ball just barely made it up. Didn't even go 1 foot out of the hole. It went 0.87 feet out of the hole. Number 5 says, when did I catch the ball? Now remember, you threw the ball at -7. So I want to know, how long does it take to go up and then back down and hit 7? Well, there's no way to find a y value on using your calculator unless you guess, but you can use a table. So if you push second and then the graph button, above the graph button it says table. So second table, we can go through this table and we can look and find where y equals -7. And y equals -7 when x is 6. So I caught the ball after 6 seconds. Okay. So now for the next one, clear that. Suppose a quadratic equation touches the x-axis at 3 seconds and at 6 seconds. Can you create a quadratic equation that fits the information above? And the answer really is no. We know that in order to create a quadratic equation, so this is no, we need 3 points. So that's the answer to number 7. We need 3 points to create a quadratic equation. But there actually are quadratic equations that go through 3, 0, and 6, 0. So I could draw some. Here's one. And here's another one. And there are an infinite number of quadratic equations. Okay? So if I had a third point, let's say that I gave you the point right here, which is 1, 9, in addition to these 2 points, then I could guarantee that this was the quadratic. But without that third point, I don't know which quadratic there's going to be. However, I can create sort of a generic equation. Generic meaning, in general terms, I can make one that fits. There are an infinite number, but there's a really easy way to make one that works. So, look at number 8. What are the roots of a quadratic? And those are the x-intercepts. So this point 3 and this point 6, those are called roots because they're the x-intercepts. Number 9 asks, what are the other names for roots? Well, they're also called zeros or solutions. We talked about zeros yesterday. They're called zeros because that's where y equals 0. Today we're going to learn why they're called roots. Number 11, create a quadratic satisfying those 2 roots. So we want to make one equation that works. And the way you do it is a little bit tricky. So my roots are x equals 3 and x equals 6. So write those down. What I want to do is take those roots and set them equal to 0. So I want this number to be a 0, and I want this number to be a 0. So in order to do that, I'm going to move the 3 over, and I'm going to move the 6 over. Well, the only way to turn a 3 into a 0 is by subtracting 3. So I get x minus 3 equals 0. On the other side, subtract 6, and I get x minus 6 equals 0. Now, we're going to end up putting parentheses around those. And I want to make some notes. These are called roots. Roots because we can actually sort of grow a quadratic out of these numbers. If I know those numbers, then I can create a quadratic. Well, once I set the roots equal to 0, I create what are called factors, and this is really important. Don't forget that. You need to know the difference between roots and factors. Roots say x equals a number, and factors say x minus something or x plus something equals 0. Roots equal a number, factors always equal 0. Well, I'm going to take those 2 factors, and I'm going to times them together. So x minus 3, multiply that by x minus 6. And when I multiply those together, I will get a quadratic equation, and that quadratic equation will hit the x-axis at 3 and at 6, guaranteed. So we have to go back to our rules of distribution. So I'm going to multiply x times x, which is x squared. And I'm going to do the first term times the last term, so minus 6x. Now, I'm finished with the first x. Now I move on to the negative 3. Negative 3 times x is minus 3x, and negative 3 times negative 6 is plus 18. Now I can simplify this. I can combine like terms and put together my negative 6x and my negative 3x, and I get an equation that says y equals x squared minus 9x plus 18. And just to show you, go into my y equals. Let's graph this equation. So graph x squared minus 9x plus 18. X squared minus 9x plus 18. Graph. And that is a quadratic that hits the x-axis at 3 and at 6. So number 11 says, is this the only quadratic that has the given roots? And the answer is no. There are an infinite number. But the nice thing is, every other quadratic that hits these roots can be created using the quadratic we just made. So if I take x squared minus 9x plus 18, if I times the whole thing by 2, then I will create a quadratic that is twice as skinny as the quadratic that we had before. So you don't need to do this, but just watch. So that would be 2x squared minus 18x plus 36. I'm going to go into y equals. If I graphed 2x squared minus 18x plus 36, and I push graph. Now this one is twice as skinny as the one before. Okay, well, if I take this and I divide it by a number, so x squared minus 9x plus 18, if I divide this by, say, let's divide it by 9, so I would get 1/9 x squared minus 1x plus 2. Now I'm going to get I'm going to get a quadratic that is 9 times fatter than the original quadratic. So you see that that one is really wide. We say that making a fraction creates a fatter graph instead of a skinny graph. If I want a parabola that opens down instead of up, I times it by a negative number. So if I did negative 2 times x squared minus 9x plus 18, that creates the quadratic negative 2x squared plus 18x minus 36. Now this quadratic is going to be twice as skinny because I'm multiplying by 2, and it's also going to flip upside down because I made everything negative. So I'll put that down in my y4. So negative 2x, negative 2x squared plus 18x minus 36. Graph it. It should be upside down, and it should be skinnier than my original. So this quadratic that we created is sort of the basis for all other quadratics, and it's going to look something like this. X squared minus 9x plus 18, and that is the most basic quadratic that hits both 3 and 6. All of these other quadratics are created by multiplying this quadratic by a constant. If you multiply by a number bigger than 1, then the quadratic becomes more skinny. If you divide it by a number or multiply by a fraction, then the parabola gets wider. If you multiply it by a negative number, then it's going to end up flipping upside down. All right, so number 12. Let's practice a few problems before we work on the assignment. So for number 12, I want to create a quadratic that hits 2 and negative 7. So I need to write down the roots. X equals 2 and x equals negative 7. Then I need to create the factors. And the factors are made by setting both of those equal to 0. So here I'll subtract 2, and there I'll add 7. X minus 2 equals 0. X plus 7 equals 0. And then I take the two factors, and I multiply them together. So x minus 2 times x plus 7. First term times first term is x squared. First term times second term plus 7x. Negative 2 times x is negative 2x. And negative 2 times 7 is negative 14. Then you can usually put those two middle terms together. X squared plus 7, 7 minus 2 is 5. So plus 5x minus 14. And this is a quadratic that hits at 2 and negative 7. Then if you wanted to adapt the quadratic, you could. You can multiply it by any number you wanted to make it skinny or fat. This is the most basic quadratic that fulfills those two roots. Number 13 is a little bit more difficult because we're dealing with fractions. So my roots are x equals 4/5 and x equals 1/3. I set them both equal to 0, and I get the factors x minus 4/5 equals 0 by subtracting 4/5. And over here I'm going to subtract 1/3, and I get x minus 1/3 equals 0. And multiplying these looks really hard, but you can just use your calculator to do it. So x minus 4/5 times x minus 1/3. First one's easy, x squared. Second one's easy, minus 1/3 x. The next one is minus 4/5 x. And the last one is a little bit tricky. You want to multiply negative 4/5 times negative 1/3. Let's use our calculator to do that. So parenthesis negative 4/5 times parenthesis negative 1/3. And I push enter and it gives me a decimal. But I don't like decimals. If I can turn it into a fraction, that's better. So push the math button, which is right underneath the green alpha key. And the first one says triangle fraction. And if I choose that, it will turn my answer into a fraction, which is 4/15. So when I multiply those together, I get the answer positive 4/15. All right. This quadratic actually works. If I were to graph it, it would hit at 4/5 and at 1/3. The only problem is we don't really like polynomials with fractions in it. And in this chapter, all I really care about is that it hits in the right places. So I just want to make sure that these two numbers are correct. So I'm going to take this quadratic, and I'm going to alter it in such a way that all of the fractions disappear. So what I'm going to do is I'm going to make a more skinny graph that still hits the roots like they need to, but the equation is going to look a lot nicer than this one. And the way you do this is you always multiply by the denominator of the constant. So I'm going to make this graph 15 times skinnier, and when I do that, all of the fractions are going to vanish. And it will always be that last number. It will always be the multiplication of the other two denominators. So this one's a 3 and that one's a 5. This denominator is 3 times 5. And sometimes the fractions might simplify, which isn't a big deal. If they do, it won't really matter. So I'm going to take this 15, I'm going to times it by the entire quadratic. X squared minus 1/3 x minus 4/5 x plus 4/15. Now I'm going to multiply this 15 into all four of those terms, and then I'll simplify it, and I'll get a quadratic that's a lot easier to work with. So 15 times x squared is 15x squared. 15 times negative 1/3, well, I don't know what that is. Let's just ask the calculator. 15 times negative 1/3, enter, it's negative 5, which is what I wanted. I wanted the fraction to go away, so negative 5x. The next one, 15 times negative 4/5. Again, I don't want to do that in my head. 15 times negative 4 over 5, enter, is negative 12, which is good. The fraction went away. Minus 12x. And then the last one, 15 times 4/15. Well, if I do 15 times 4 over 15, 15 cancels 15, and the answer is just 4. And that will always happen. On your constant term, the denominator and the numerator will cancel, and you're just left with that plus 4 or whatever it is. Okay, so now I can put these together because they're like terms, and I get, let's just a different color, 15x squared, negative 5 and negative 12 is negative 17x plus 4. And both of these quadratics, this one here and this one here, they hit the x-axis in the same place. The roots are 4/5 and 1/3, but this second one has no fractions in it, and we prefer to use that when we can. So your assignment today is to create quadratics on all of these problems. The answers are there, so you need to show your work. If you don't show your work, then you don't get any credit. And notice the last 3 problems do have fractions, so make use of the fraction button on your calculator, and when you're done, multiply the entire quadratic by the denominator of the last term, and all the fractions will disappear. Okay, good luck.